All right, continuing on, 1996, question 4, free response. We just looked at how to do part A, which led us through series circuits. And now we're going to check out part B, which is going to lead us into parallel circuits. So using all these components, draw a circuit diagram in which each resistor has a non-zero current flowing through it, but in which the current from the battery is as large as possible. And so what they're secretly saying there, as large as possible, they're saying, hey, since electricity takes the path of least resistance, you're going to have more current with less resistance. So we want to have the equivalent or total resistance to be as small as possible. And so how can we wire this so that the total resistance is as small as possible? We're going to wire each of them in parallel. Offering more paths to that electrical traffic gives you less resistance overall. And so let's draw that. And as you would be done as soon as you drew this, that's all they wanted you to do. But we're going to do a lot more exploration with it so that we can learn more about parallel circuits. So basically, you want to give the electricity 4 different paths. You want to give it its own path for each resistor. And so the way to draw that, there's a couple ways, but here's one. Here I'm going to give a path for the first resistor. And then I'm going to make a junction here, split the wire, and give it another path for this resistor and bring that back together. And then I'm just going to give it another path for the third one and bring that together. And then I'm going to give it a fourth path and bring that together. And then to make my circuit look really ugly, I'm just going to use this blue color to show you all the different loops that you've just created. So your total current could come out of here, and then some of it could go this way and come back. Or it could go out of here, and then some of it could keep going and go down here and come back and recombine and return. Or it didn't have to split there. It could have kept on going and go through here and come back and recombine. Or it could have kept on going and then come back here and recombine. And so there's 4 different paths. 1, 2, 3, 4. And then I'm going to get rid of that because that's really ugly. But that's the way that you could view it. Another way to correctly draw this would be to do something like this. We could do the total current coming out here, and then we could split it, boom, and go 1, 2, 3, 4, and then just put the resistors on their own paths. And then just bring them all back together, boom, and run that back to the battery. And that would actually be the exact same, as far as the battery is concerned, that would work the exact same way as what we drew earlier. You don't see this drawn this way very often because it's a little bit uglier, just aesthetically. It's not as pretty, but some people just like to see, it makes a connection for them. So I'm going to draw mine like this, but you're welcome to draw yours the other way. Okay, and then let's go ahead and label these. So this would be R1, R2, R3, and R4. And then let's put the values where we can. So we know that this is a 12-volt battery. That's our total voltage, or our EMF, with that epsilon there. Then R1 was 100 ohms, R2 was 30 ohms, R3 was 20 ohms, R4 was 10 ohms. And then let's just go ahead and do our VIR chart, and we'll stick to that navy blue from earlier, and we'll make a VIRP chart. We'll do the V, the I, the R, and then have the extra column for the P. So V equals I times R, and then the power, and we'll leave the power alone until the end, a VIRP chart. And then make a row for each resistor like we did before. So we have R1 row, R2 row, R3's row, R4's row, and then we have the totals row, TOTALS. And finish with your lines. Isn't that beautiful? And now make your columns, column for V, column for I, and a column for R. And now let's fill in what we're given to start with. We have that 12 volts here in the total voltage part. And then we have all the resistances. So R1 is 100 ohms, R2 is 30 ohms, R3 is 20 ohms, R4 is 10 ohms. And now the real common strategy is to go ahead and get your equivalent resistance, your total resistance. And by the way, the only reason why we're doing this is just to learn more about working with these parallel circuits, but you would have been done by the time you finished your drawing, your diagram there. That's all they wanted you to draw to finish this part. But we're going to learn some more. So we're going to do the VIR chart, then we're going to do the highlighting, the voltage, the coloring, the voltage drops, and then we're going to rank the light bulbs by their brightness and see if we can expose something about taking the same light bulbs but wiring them differently, and seeing what happens to their brightness. So we're going to add the resistances inversely because parallel will, you're going to add your currents in each branch, you're going to have the same voltage drops, and you're going to add your resistances inversely. And so let's do that. So we're going to have the equivalent resistance. I need to get a little spot here to do that. So let's do that maybe underneath the circuit here. So we're going to have Req, or R total, is going to equal parentheses 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. And then all of that to the -1 power so that we inverse the total as well. And let's go ahead and substitute in our values. So we're going to have 1 over 100 ohms plus, I'm going to leave the ohms out, otherwise I won't be able to fit this, 1 over 30 ohms plus 1 over 20 ohms plus 1 over 10 ohms, fitting that in there to the -1 power. Now we have to find a common denominator, if I say it correctly, just having a little fun there. I'm going to use 300, so I'm going to have 3 300ths plus 10 300ths plus 15 300ths plus 30 300ths, all to the -1 power again. And we add those together, you have 10 plus 15 is 25, 25 plus 30 is 55, and 55 plus 3 is 58. So we're going to get 58 300ths to the -1 power, and then when you go ahead and take it to the -1 power, you're going to get 300 over 58. And I'm going to go ahead and calculate that. 300 divided by 58 is 5.17, rounding it to the hundredths place, 5.17 ohms. All right, so we finally got our equivalent resistance for the whole circuit, 5.17 ohms. I'm going to put that here in my resistances column. And now that I've collected the total voltage and the total resistance, I can use VIR to calculate the total current that is flowing out of and into the battery. And so I'm going to divide 12 divided by 5.17. 12 divided by 5.17 is a total current of 2.32 amperes. Now, just referencing that back to when we wired these exact same resistors in series, look at the current that was flowing in series up there at the top, 0.075 amps. And they're the exact same resistors. We've got a lot more current flowing here, 2.32 amps. So your battery is going to run down faster as it's giving you more current. But your light bulbs are going to be brighter. So that's the trade-off. And we're going to see that when we get the powers. The powers are going to be much higher than they were before. But before we can get there, we have to finish this out. So what's the same in parallel? The same that everyone in parallel has is not the current, but this time it is the voltage drops. So we know that every single light bulb is going to be experiencing the total of 12 volts dropping over it. So we can just go ahead and fill that in for everyone, and then that unlocks each of the rows, because we can then use VIR to calculate the current that splits and goes through each branch. And so we're going to do 12 divided by 100, and that's going to be 0.12 amps are going to go through the 100 ohm branch. And remember that electricity likes to take the path of least resistance. And so this is going to be the least amount of current taking this highest resistance path. The R1 path has the highest resistance with that 100 ohms than anyone else. And actually it's going to be proportionate. We'll see that as we go ahead and calculate it. So then we have 12 divided by 30 is going to be 0.4 amps. And then 12 divided by 0.2, oh no, 12 divided by 20 is going to be 0.6 amps. And then 12 divided by 10 is 1.2. We can just move the decimal over. Now the currents should add up, just to double check, the currents should add up to the total. And so 0.12 plus 0.4 plus 0.6 plus 1.2 does add up to 2.32. So that's a nice way to double check our answers, that the whole VIR chart is connecting with all the rules that it follows. Now let's do the same thing we did before where we colored in the voltage drops. And so let's color in the voltage drops, but this time you're only going to need 2 colors. I'll start with red and I'll drop all the way down to purple because each time the current is going to experience a drop of energy, it only gets to drop once. So the current that goes in the inner loop is going to drop from red all the way down to purple across that 100 ohm resistor. It's going to experience that full 12 volt drop there. And then just keep coloring your other paths. And so we keep on the current that went this way, which was the 0.4 amps going through R2. It drops its 12 volts, goes red all the way to purple, and then recombines there at that junction. And then again and again. There we go. And so you can see the same color change across each parallel branch, and that represents the same voltage drop, or the same potential difference. And so each time, a little hairy if I use the green in between each of those to represent our little drop here, but our change in voltage, just to zoom in on there, our delta V, for all of them, I could put a 1, a 2, a 3, or a 4, but it's the same for everybody, is going to be a negative 12 volt drop, and that's represented by that color change of red to purple. So that you start in the red at a potential of positive 12 volts everywhere across the top of this drawing, and then you end up in the purple at your perfect obeying Kirchhoff's loop rule of positive 0 volts. So you're obeying the law of conservation of energy, and you used up all your energy no matter which loop you took. Take the inner loop, or one of the middle loops, or the far outer loop, you still dropped all your energy. Okay, let's rank these by power, and then we've done everything we can do that you have to be able to do in AP Physics 1 with this circuit. So again, we're going to use the this darker yellow color for our power, and we're going to use Joule's law for our power. And so to zoom in on my power column here, P equals I times V. And so we're going to multiply the I's and the V's for each row to get all the power values. So then we have 12 times 0.12, which is going to be 1.44 watts. And then we have 12 times 0.4, which is going to be 4.8 watts. And then 12 times 0.6, which is 7.2 watts. 12 times 1.2, which is 14.4 watts. And then if you add those all together, you should get the total power. And you can double check by multiplying 12 by the total voltage drop by the total current, which is 12 times 2.32, we get 27.84 watts. And if we add 1.44 plus 4.8 plus 7.2 plus 14.4, we get the exact same number, 27.84. So another way to double check our work. I love it. Now let's rank them by brightness. So the brightest to the dimmest ranking by power. And so we have the order is actually the opposite than it was before. We're going to have R4 be the brightest, greater than R3 with a power of 7.2, and then R2 has a power of 4.8. So that's the next one. And then R1 has a power of 1.44. So R1 is the dimmest, and R4 would be the brightest. And then if you compare that to earlier, when we wired them in series, you can see there at the top, the ranking was exactly the opposite. So in parallel, the light bulb with the lowest resistance is going to be the brightest because it's going to have the most current flowing through it at the same voltage. Whereas in series, the light bulb with the greatest resistance is going to be the brightest because it's going to have the same current, but it's going to be dropping more voltage. Okay, and that's how to do parallel. The next thing we're going to look at is part C. We're going to look at how to do combination circuits.